Now, let us further confirm the particle nature of light, the particle nature of electromagnetic radiation. Compton effect is the basis to add in addition to Planck's blackbody radiation law and the famous photoelectric effect. Both photoelectric effect as well as Planck's blackbody radiation law can, can be explained by virtue of assuming that light is made up of the quantized energy packets. Uh, so now, to further support the fact that under certain circumstances that the light behave as made up of quantized uh, or the packets of energy, and the magnitude of each packet of energy is given by Planck's equation. So it was basically Compton who discovered that when a monochromatic beam of uh, high frequency radiation, say for example, we can choose X-rays, we can choose gamma rays. So when this monochromatic chromatic beam is scattered by a substance, so if we have a substance, the scattered radiations contain the radiations of lower frequency or greater frequency, along with the radiations of unchanged wavelength or frequency. So the radiation of the unchanged wavelength in the scattered light, they are called basically unmodified radiations, while the radiations of greater wavelength are called modified radiations, and this phenomenon is called as Compton effect, and this effect, this Compton effect, was explained on the basis of quantum theory of light, and according to which what we know is that according to the quantum theory of light, to which the radiations consist of the particles known as photons, and each photon having an energy equal to h nu, and h is what's called as Planck's constant, and nu is the frequency of the radiations. Now, what happens is that we have the photons. What they do, these photons, they move uh, with a velocity equal to the velocity of light. They possess momentum, and they obey all laws of conservation of energy as well as momentum when they strike with the electron. So if I assume here this is an electron, and if I assume that I have a radiation, and this radiation interacts with this electron. So so according to the quantum, I mean, sorry, according to this Compton, the phenomenon of scattering is due to the collision between these two particles. One is a photon, and another is electron. So one photon of incident radiation, and other is an electron of the scattering substance. Now, when the photon of energy h nu, so suppose this is a photon, when this photon of this energy collides with a free electron of scattering substance, uh, initially at rest, it transfers some energy. It transfers some energy to the electron. Due to this energy, what happens to this electron? This electron gains kinetic energy, and recoils with some velocity, what we may call as v. Hence, then we will have a scattered photon. So we have an electron. Let's assume that this electron moves in this direction, and we may call this as a recoil electron now. And this recoil electron, and we have a scattered photon. So let me choose a straight line for this so that make it geometrically consistent. So we have a scattered photon, and this photon will have lower energy. That means this photon will have frequency lower than that of the frequency that it possessed. Or we can say it will have longer wavelength than the incident one. And this phenomenon is called, so here we have a photon of longer wavelength. This phenomenon is referred as Compton effect. So what are the basic assumptions here? is that this Compton effect is a result of interaction of individual photon and a free electron. So the electron is assumed to be free inside the substance. And the next important point is that the collision is relativistic. This collision is relativistic and also elastic. And the next important point is that the law of conservation, the laws basically, the laws of conservation of linear momentum and uh, uh, and energy, they hold good for this formalism. Now, to go with it, what we have a photon. Let's have a photon of all energy equal to h nu, and it falls on the surface of some substance where the electron is assumed to be free. What it does, it scatters this, it collides with this electron, it scatters it, and assuming this electron to be at rest. And during the collision, it gives a fraction of energy to this free electron. Thus, the free electron gains some velocity and it recoils. And after the collision uh, led, the scattered photon that we have a scattered photon and a recoil electron, and they make angles with the original direction of the photon. So let us assume that this angle is phi, and this angle is theta. So theta is the angle between the recoil electron and the original x-axis. So this is my x. Okay, so this I will choose as my y. All right. So now, before the collision, what's going on here? So what's going on here before the collision? We have the energy of the incident photon, that's h nu, and the energy of the electron is m naught c square. And what is m naught? That's the rest mass of the electron when it is moving with the velocity equal to v. And this the momentum of the incident photon is, so if energy is h nu, its momentum is going to be h nu by c. And the momentum of the electron before the collision is zero because it's not interacting. So what we have here, we have momentum before the collision. So I should write here momentum before collision. Yeah, that is h nu by c. And the momentum, this is basically the momentum of the photon before the collision, and the momentum of the electron before the collision is zero. And after the collision, what we have is the energy of the scattered photon. What is that? That's h nu dash. Okay, assuming nu dash to be the energy of the photon after it interacts with the electron, and the energy of the electron will be simply mc square. And this m is the mass of the electron when it's moving with the speed of light. So the momentum of the scattered photon. So here we have momentum before the collision for the photon, and we will have momentum of scattered photon. So what will be that? That will be h nu dash by c. So the momentum of the recoil electron, that will be mv. Multiply this mass with the velocity of the electron. So what we will say here is that the energy of the system, I mean electron and photon, uh, before the collision. So what will be the energy of the photon and electron before the collision? That will be simply h nu and m naught c square. So I will say momentum. Sorry, the energy before collision. What will be that? That will be h nu plus m naught c square. And the energy after the collision. So what will be that energy? That's going to be h nu dash. Okay, this is h nu dash plus mc square. Right. So we can use the principle of conservation of energy. So what will that give us? So this must be h nu dash. So that will give us h nu plus m naught c square is h nu dash plus mc square. So from this equation, I can think of mc square equals h nu minus h nu dash plus m naught c square. All right, so let me call this one for the time being. And now we'll be looking for the conservation of momentum. So for momentum, we will have momentum along x-axis, and we will have momentum along y-axis. And if this is phi, then we will have here h nu dash by c sine phi. And along x, we will have h nu dash by c cos of phi. So this is how it will work. So for mv, we will have this will be mv sine theta, and along x we will have mv cos theta. And what is important here is that we can write down the linear momentum along x-axis, the conservation along x-axis, then we can write down the conservation along y-axis. So we can see clearly that the vectors that are representative of the momentum along y-axis, they are opposite to each other, and their resultant has to be zero. So we can write down now, so we will be looking for conservation of linear momentum. So one will be along x-axis and another will be along y-axis. So we will have these two cases over here. So we already have some equation. Okay, so we have equation 1 here that's for the conservation of energy. Now, so what we will write along x, it will be h nu by c plus 0 is h nu dash by c cos phi plus mv cos theta. So this will be along x. And what will be along y? Along y, it's going to be mv cos theta. Along y, we will have mv sine theta. It's not cos theta. Along y, it has to be in terms of sine theta. So here we would like to have rearrangement first. So we can write down here mv cos theta is, even this c will come up. So cmv cos theta will be h nu minus h nu dash. Okay, so let me call this as equation 2 for the time being. Now, I'll be writing the conservation of linear momentum along y-axis. So that certainly will be mv sine theta is equal to h nu dash by c sine phi. Okay, it was in the diagram itself. Clear. So it is mv sine theta minus h nu dash sine phi is equal to 0. So from this, what we'll get, we can write down, this c will come here, so we can write down mvc sine theta is h nu dash and sine phi. Now, choosing this as equation 3, and what we'll do is we'll be scaring and adding equation 2 and 3. So we'll scare them. So if I scare this and I add, so that it's clear from left hand side, what I'll have m square v square c square times sine square theta plus cos square theta. But sine square theta plus cos square theta is 1. So so what I'll have m square v square c square equals, then we will have the square of this, and then we will have the square of this. So if I have to write down the square of this, I can write down it. You can do it. So that will be h square times. We can write down as a whole thing first. So this is h nu minus h nu dash. Maybe I'm losing something here. Yeah. No, that's fine. So here I am missing something because I'm not taking into account this cos theta is okay, but here it is cos phi. Okay, so h nu dash cos phi whole square plus h nu dash by c sine phi whole square. Now this is the story till now. Now let's see where we move from here on. So we can write down after this what we will have m square v square c square is. So now h square I can have out. So a square will give me new square, b square will give me new dash square, minus twice new dash cos of phi. Okay, so this will be my result, and you can check this result as well. You can boil down this equation. You can boil down this equation to the result that's obtained here. So uh, now let's go back to this equation. Where is that equation? Equation 1. Yeah, this is my equation 1, and what I'll do is I will be squaring this equation. So let me call this for the time being equation 4. So squaring equation 1. So what will I get here is m squared c to the power 4. So m squared c to the power of 4, that will give me h squared, yeah, new square plus new dash square minus twice new dash plus twice h m naught c square new minus new dash plus m naught square c to the power of 4. So this is what we'll get when we will have squaring on both sides to this equation. So you can do this algebra. It's very simple algebra that you can do it easily. Nothing wrong with that. So you'll come up with this equation. So we have equation 4 and we have equation 5, and I'll call this 5. And what would I like to do is I will subtract. So subtracting 4 and 5. And what we do is we get m square c to the power of 4 minus m square v square c to the power of square is equal to. And you will have all the formal cancellations here, and what will be left with is twice h square m times new dash times cos phi minus 1 plus twice h m naught c square times new minus new dash plus m naught square c to the power of 4. Now this is my equation number 6. Okay, so we have subtracted this equation with this equation. Now let's go back to, and this is the result that we have obtained. Now, according to theory of relativity, what we have is we have m equal to m naught by under root of 1 minus v square by c square. And if we square it both sides, it will be m square is equal to m naught square by 1 minus v square by c square. Okay, so what we are left with, we're left with this equation. This is the result that we have obtained by subtracting 4 and 5. And here we can think of using this this m, the relativistic m will be replaced by this equation. So if I do that, what will I obtain is I will obtain m, this m square c square minus m square v square c square. So this I can write down as this will be m naught square by 1 minus v square by c square, and I have original c square here, minus, then I will have this m, this is c to the power of 4, it's not square here, this is c to the power of 4, so this is c to the power 4, so this will be c to the power 4. Then what I'll have here is minus m naught square by 1 minus v square by c square. All right, so then I'll have c square here, and the original v square. So I can think of getting m naught square c to the power of 4 out. So if I do that, what I'll get is I'll get 1 by 1 minus v square by c square minus, okay, c to the power of 4. So I'm getting c to the power of 4 out. So what am I going to write here is v square by c square divided by 1 minus v square by c square. All right, if we multiply this back, we'll get the back. We'll come back to the original term over here. So, uh, so we'll have in the denominator 1 minus v square by c square. So in the numerator, we'll again have 1 minus v square by c square. Okay, this has to be observable. So here I'll have m naught square c to the power of 4. Now this term and this term will cancel. So the result of this term, these two terms, will be m square c to the power of 4. So we'll be using this in the original equation that we have obtained. Yeah, what's that? So instead of this, I'm going to write m naught square c to the power of 4. Then I'm going to write the right hand side. So what's that? That is twice that's twice h square nu dash times cos of phi minus 1. Okay, then plus twice h m naught c square times nu minus nu dash, then plus m naught square c to the power of 4. So it's clear that these two terms are going to cancel from here. So we can boil down this so this h can be out. So we will have the equation twice h times nu minus nu dash times m naught c square. This will come out to be minus twice h square nu dash times cos of phi minus 1. And we can rearrange the terms. This h and h will cancel, h and square will cancel, this 2 and 2 will cancel, and we will be left with nu minus nu dash by nu dash is equal to, if we take this minus inside, what will be left with is h by m naught c square times 1 minus cos phi. So we can write down this as this will be 1 by nu dash minus 1 by nu is equal to h by m naught c square 1 minus cos of phi. So uh, this h is the Planck's constant, m naught is the rest mass, and c is the speed of light, and they are all positive. So if they're all positive, and we can have the maximum value for cos phi equal to 1, and this equation indicates that this nu dash is less than nu. So what is nu dash? It's the frequency of the recoil photon, and what's nu is the frequency of the original photon that's interacting with the electron, which was assumed to be at rest, and uh, and this frequency of the scattered photon is less than that of the frequency of the incident photon. Now we can translate this equation, this Compton effect, this Compton equation in terms of wavelength also, and for that what we are going to do is to replace nu by c by lambda and nu dash by c by lambda dash. So we can do that, and what we'll obtain, we will obtain in that case lambda dash minus lambda is h by m naught c. The square term and c will cancel when we'll be using for nu and nu dash times 1 minus cos of phi. Now, what am I trying here is that this relation gives us the change in the wavelength of the incident photon. And what it indicates that lambda dash is greater than lambda. And what it means is that the scattered radiation that we have, this is the scattered radiation, okay? So this is over h nu dash. This is indicative of this fact that this scattered radiation has greater wavelength than the incident one, and from this equation, it's clear that the change in the wavelength is independent of the frequency of the incident photon. It does not depend on the frequency of the photon as well as the nature of the scatterer, but it only depends on this cos phi. It has a dependence on this angle of scattering, what is chosen as phi. So, so as the angle of scattering, this if this angle increases, cos phi decreases, uh, and for phi equal to pi by 2, we have cos of phi equal to 0. So what will happen in that case, this delta lambda, which is basically lambda dash minus lambda 1, it's going to be equal to h by m naught c. And we can use the values of the constants, Planck's constant, rest mass of electrons, speed of light, and by doing so, this value comes out to be 0.02426 angstrom. And this is called as Compton wavelength of electron. So this is the Compton wavelength of the electron. Now, so what can be the maximum value? I mean, the maximum value will be for cos of phi equal to 180 degree. This is going to give us the maximum value, and that value is going to be equal to 2, because cos of 180 is minus 1. So 1 minus cos phi is going to give us 1 minus minus 1 equal to 2. So that the maximum wavelength change that can be possible in terms of this Compton wavelength is it will be roughly of the order of 0.05 angstrom. So from this equation, I mean, what it follows that from this equation, it follows that the Compton effect can most readily uh, detected for radiations of whose wavelengths are not greater than a few angstrom units. I mean, what I'm trying to talk about here is, for example, if we choose the wavelength equal to say 5 angstrom. Okay, so the maximum change in the wavelength with respect to this is going to be of the order of 1%. While if I choose lambda equal to 1 angstrom, then the effect will be nearly 5%. So for visible light of whose wavelength is of the order of 5,000 angstrom, this suggests that the maximum wavelength change will be 0.05. It will be nearly equal to 0.05, and it's only about if we measure it, it's only about 0.001% of the incident wavelength, which is basically undetectable. So what am I trying to tell here is that the Compton effect cannot be observed for visible light rays. So in the theory that's out there, what we have assumed is that the electron is so loosely bound to the atom that it can be regarded as a free particle. But in reality, it's not so. The electron is bound to the nucleus, so electron is tightly bound to the nucleus. So if this is the nucleus, we have electron, it's bound to the nucleus, and it's bound overall to the atom. The atom as a whole recoils. So when we have the interaction of the photon, the whole atom recoils as a result of Compton scattering. So the conversion of the equation that we have, say, for example, the equation that we have, the equation that we have is lambda dash minus lambda is h by m naught c 1 minus cos phi. So what is important here is that we have to replace the mass of this electron with the mass of an atom. Okay, so if I choose, for the sake of argument, if I choose the simplest of atoms, if I choose hydrogen atom, then for that, this for phi to be maximum, this h by m naught c, which is basically m of hydrogen, it nearly comes out to be 4.9 times 10 to the power minus 7 angstrom. So what am I trying to say here is that what we have is in reality this electron is tightly bound to the atom. So for an incident wavelength of the order of few angstroms, the change in wavelength is negligible. We'll not be able to detect the change that's predicted by Compton effect for all values of phi. So this explains this can be translated into something else. What it explains is the presence of the unmodified radiation. So as we discussed, as we started our discussions, it's not only the radiations of whose frequencies are modified we obtain. In addition to the modified radiations, we obtain the radiations having no change in their wavelengths. So this can be assigned to why we are obtaining some of the photons whose energy does not change. Now, another important argument that's linked with Compton effect is the direction of recoil electron. Direction of recoil electron. So we will have the recoil electron, and how could we do that? How could we calculate the direction of the recoil electron? So for that we have our original diagram. So what we have something like this. Okay, so this was my theta, this was my phi, and this direction can be calculated by tan theta. So tan theta will be, h nu dash sine of phi divided by h nu minus h nu dash cos of phi. All right, so this is my theta. All right, and this will come out to be, if I change it, so these h's will go down, so nu can be written in terms of lambda. So you will have c by lambda dash sine phi divided by c by lambda minus c by lambda dash and cos phi. So this c and c will also cancel. So what we will come up with is lambda sine phi divided by lambda dash minus lambda cos phi. So this is my tan theta. So this will give me the recoil, the direction of the recoil electron. And we can also calculate the kinetic energy of this recoil electron. So what could be done for that is kinetic energy of a recoil electron. So for that, what we have, this kinetic energy will be m minus m naught times c square. So this is basically h nu naught dash h nu minus h nu dash. And this equation is already obtained for the change in kinetic energy. So from here, what we can obtain is we can obtain hc by lambda minus hc by lambda dash. So hc can be out inside 1 by lambda minus 1 by lambda dash. So we can have hc by lambda dash minus lambda. So this is going to give me the kinetic energy. And if I use the results of Compton equation here, because lambda dash minus lambda, so I can obtain, my result can be written as, say, lambda dash minus lambda is h by m naught c times 1 minus cos phi. So if I translate this lambda on the other side, this lambda dash will be lambda plus h by m naught c times 1 minus cos phi. So we can retranslate this equation in terms of frequency. So we can use nu equal to c by lambda, and what will come out of there is we will have c by nu dash is equal to c by nu plus h by m naught c times 1 minus cos phi. Okay, so this c can be modulated. I mean, we can take the c down here, so we'll have 1 by nu dash equal to 1 by nu plus h by m naught c square 1 minus cos phi. So we can think of writing nu dash here, and that will be equal to nu by 1 plus h nu by m naught c squared times 1 minus cos phi. All right, so we can use some symbols. So this is nu by 1 plus, I will replace this thing by, say, y times 1 minus cos phi. Okay, so this is my nu dash. So what would I like to do is I would like to use the value of this nu dash in the equation here, in the equation of kinetic energy that I started with. I would like to use that. I'd like to use that here. So T, this is my K kinetic energy. So what will be kinetic energy? So I will use this nu dash in my equation. What is that? K is equal to h nu minus h nu dash. Okay, so what is this? So K will be h nu minus h times nu by 1 plus y, 1 plus y times 1 minus cos of phi. This should be it. So now h nu can be common from both. So what will remain inside is 1 minus 1 by 1 plus y times 1 minus cos phi. We can proceed from here. So this will be h nu. We can have LCM 1 plus 1 times 1 minus cos phi. So here we will get this here, and then this minus will mean there, this plus 1, and so 1 plus y times 1 minus cos phi minus 1. So minus 1 and plus 1 will cancel, and we will get the final expression for the kinetic energy of this recoil electron. This kinetic energy will come out to be h nu times y times 1 minus cos phi divided by 1 plus y times 1 minus cos phi. So this will be my final expression for the calculation of the kinetic energy of the recoil electron.